Well, welcome to this recording of the static electricity and plastic natural gas pipe O&M operations hazard and control. My name's Dirk Smith, and we're going to get started with this. See if we can't have a meeting here. Now, as we get started in this, I just want to set the overall regulatory framework. You know, the LDAR rule was paused on January 20th, 2025, the inauguration of Donald Trump. However, it's important to remember the Pipes 2020 Act is still enforced. It is a congressional mandate, and you cannot just, the executive branch can't just overrule a law. But it's important to keep in mind two additional factors that have been added to the pipeline safety environment on a federal legislative basis. And that is now that you must take into account environmental effects of natural gas leaks in operation and the health effects from natural gas operations. Both of those are designed to reduce leaks and to improve integrity. Now, there's going to be the goals of this session. The first thing I want to do is gain a working understanding of static electricity and PE pipe. The second thing is to understand the four threats that static creates in your gas field operations. The third thing is we're going to do is going to review available static suppression technologies. And then finally, we're going to talk about some best practices. Now, it's important that we thank you for your interest in this topic, static electricity and plastic natural gas pipe O&M operations, hazards, and controls. My name is Dirk Smith, president of Ionix Gas Technologies. This is the recording of the presentation I made on September 30th. It's important we keep in the regulatory framework of this presentation. That's Pipes Act 2020. Now, the LDAR rule was withdrawn from the Federal Register on January 20th after the inauguration of Donald Trump. However, that does not negate the Federal Pipes Act. And in the Federal Pipes Act, in addition to improving safety, which is an existing mandate that PHMSA has, the enforcement agency, it also said that they must take into account environmental effects and health effects of methane emissions. And so that's going to be the basis of what we're going to be talking about. That's going to be the overall framework. The goal of this session is to gain a working understanding of static electricity in your PE gas pipe system. We're also going to do a digression about metal pipe. And then we're going to learn to recognize the four static threats that come about due to static electricity in your distribution systems. We're going to review available static suppression technologies, and we're going to suggest best practices for that. Now, it's important we all have the same understand the same terminology. So the first thing is to understand what static electricity is. Electricity is electricity. The difference between static electricity and current electricity, the electricity that's coming out of the outlet at your house that's powering this laptop I'm recording on, is that the electricity in your house, the current electricity, is flowing through a material that is an electrical conductor. That is, by nature, copper very easily allows the flow of electrons through it. However, if you took those same electrons and put them on a piece of polyethylene, they would not move. They'd be static. The reason they're static is because in the inherent nature of the polyethylene pipe, it will not allow the movement of electrons on it. Therefore, if you want to deal with this electricity, you have to understand you have to conduct it away because the material will not conduct it away. So, how is static electricity created? Well, generally, it can be created a lot of different ways, but in our case, it's due to the friction It's the passage of gas inside the pipe, the mechanical shearing action of the gas passing through the pipe. When it does so, it physically scrapes off electrons. And these electrons, displaced electrons, accumulate in random places inside your system. We don't know why they go one place and rather the other, why they're not evenly distributed. It just does. So what happens is the static starts to build up. These orphaned electrons accumulate inside the pipe in certain areas. Now, the problem with that is this. The natural world is designed to be at electrical neutrality. When electrical charges, surpluses build up, they want to arc to ground to neutralize each other, just like lightning in the sky at night in this picture. And so what's going to happen in your system, if this static builds up in your system, it's going to discharge, and that discharge can cause an ignition. It can put a hole in the pipe. It can shock a worker, and it can destroy your low voltage electronics like your meters and scan equipment. So if you don't deal with a problem, Mother Nature will take care of it herself. Now, 4 basics of static electricity and polyethylene pipe. This was research done by the Gas Research Institute. It was paid for by the industry. And this is the most important thing you need to take away today. If you have a priority of everything, if I gave you a priority of everything I wanted you to learn today, this would be number 1. The root cause of all your static issues is because static starts inside the pipe. It's the movement of gas. It's the friction in there. That's the engine. That's what's making the static. And so understand it will flow out into it'll manifest itself in different ways, but it all starts here. And here's a citation from the Gas Research Institute, what they found. The second thing is that because those electrons are sitting on a material that is not an electrical conductor, that is polyethylene, those charges just sit there. They can't conduct away. They're just going to sit there until something causes them to go away. And there's a citation from the Gas Research Institute. Now, the third thing is not intuitively obvious. I could explain it. It's take too much time. You really don't have to understand why it happens. You just need to know it does happen. And that is when the static charge is built up on the inside of the pipe, it induces a charge on the outside of the pipe. That's why you do the static discharge procedure on the outside of your pipe. And the third thing is that static's going to discharge. If these charges accumulate, they will by nature seek to dissipate themselves, to neutralize themselves by arcing to ground. And so it's important that you understand that problem is just not going to go away. Now, from these 4 basics flow 4 threats. Ignition, which is a personal injury and a property threat. Electrostatic leaks, it's an integrity issue. Static puts holes in pipe. It shocks people, and it burns out electronics, and that's an integrity. If you manage the static in your system, all these problems go away. Now, this is a bulletin issued by OSHA about static electricity and buildup pipe. It was issued, I think, in around 1980. And it was directed just to make sure that everybody is aware, that OSHA is aware that static builds up in polyethylene pipe, because they had an incident at Ignition in Dallas, Texas. In 1973, in the AGA plastic pipe material book, it advised operators to do static suppression before working on polyethylene pipe. Now, the reason I bring these 2 up to you is I got a call one time from a gas company, fairly large one, and they said, please don't send us anything more about static electricity in systems. We don't want to know about it. And I'll tell you, I was stunned. Basically, they were saying, if we don't know, if we're ignorant of the problem, then we won't be liable. The plastic pipe manual, OSHA has said there's a problem. AGA says there's a problem. If you think declaring ignorance as a defense, as affirmative defense in a civil liability case, not only will that be dismissed post haste, but you'd even be accused of negligence by not knowing some of the basics that everybody else in the industry is aware of. So you can't put your head in the sand about this issue. It will come back to bite you if you do that. Okay, of the four threats, we're going to talk about the first one, and that is the ignitions of leaking gas. Now, why do we prevent leaks? You know, everybody wants leak detection. Everybody wants to make sure we don't have any leaks. The PHMSA wants no leaks. What's the reason they don't want leaks? The reason they don't want leaks is because the leaks ignite. And your main source, your probable source of ignitions of leaks is static electricity. So remember, your leaks aren't the enemy, ignitions are. If you find and deal with the primary ignition source of leaks, leaks don't become as nearly as threatening as they used to be. This is a pie chart of the claims expense paid by the Associated Electric and Gas Insurance Services, or AGIS. AGIS insures probably 90% of the gas companies in the United States, in addition to insuring the electric. And this is a pie chart of the claims. I think it was 2023, this was given to me. And this shows where all the money were paid for claims by category by AGIS in the year 2023. If you take a look at it, they've got environmental damage, property damage, other not otherwise classed, struck, CO2 poisoning, accident, failure to supply. But all those other categories combined do not equal what they paid out in fires and explosions. It pays to prevent ignitions. This is an audio, this is a video that was sent to me. It was a recording of a TV station's evening news when it was broadcast. It's been about 25 years now. It was recorded using a VCR over the television. That's how long ago it was. But it's one of those rare instances where an ignition is caught on tape. What happens is the television station listens to the police radio. They heard there was a leaking gas line. They send a crew out to film it, and they listen to the police radio, and they just send people out. And they don't know. They collect it all up at the end of the day and decide what they're going to air. And this is what they aired on that day.
A natural gas explosion rocked an Oklahoma City neighborhood just before noon today. Workers were trying to repair a ruptured line at Northwest 131st and MacArthur when the gas ignited. Newsline 9's Heidi Browning joins us live from that neighborhood. Heidi?
Well, Kelly, there's a bit of a mess out here in the neighborhood. You can see behind me what's left of a fence, charred remnants of the posts, and quite a lot of digging that's been done to make repairs to those lines. But people coming home this evening will find a much calmer scene than what many people saw this morning. It started as a fairly routine repair job. ONG workers were trying to get the gas turned off after a 2-inch medium pressure line was accidentally cut. Suddenly, the gas exploded, sending huge flames into the air. 2 workers received minor burns. ONG officials say there's preliminary speculation that static electricity in the plastic pipe somehow caused the explosion. It took about 30 minutes to control the fire and get the gas turned off.
That is your worst public relations nightmare. It would have never made the news. Most likely, I shouldn't say never. Most likely it would have never made the evening news if it hadn't ignited. It's the ignitions that cause you the heartburn. Leaks, if they don't ignite, are just leaks. You wouldn't have burned fences if it didn't ignite. Now, you have a unique problem in distributing gas in polyethylene pipe. It is a terrific material, absolutely terrific. The one drawback is it creates its own ignition source and the transport of gas inside the pipe, static electricity. So here's what gas research says static gas ignitions actually occur. If there's an ignition of leaked or leaking gas, in the absence of a known ignition source, you must have an ignition source. Given that the passage of natural gas inside a pipe creates static, the most probable cause of the ignition is that static electricity is arced to ground in the presence of a gaseous mixture. You got to have an ignition source. In that video with those ONG guys, there was nothing static. There was no flame, sparking motors, anything like that. Where was the ignition source? You have to have one. Had to be static electricity. So In this, we're going to look at some of these field operations and what makes them dangerous specifically, because I want you to see where the danger is in these operations. You're going to know that these operations are dangerous, but where's the static in these operations that causes it to be dangerous? That's what I want you to understand. So remember, in any situation with a potential static ignition risk, you have to have interior surface static exposed, gaseous mixture, and proximity to ground, electrical ground. So here are the 5 most dangerous operations. And when your crew goes out in the morning, like this crew does, I want you to be ready and understand, explain to them what these dangerous operations are. Remember, there's going to be both the static starts on the interior of the pipe, works its way out. The root cause is in the interior. Now, this is the most dangerous one, and this is what you saw in the ONG video I showed you. There was third-party damage. Now, what happens is we know static is generated inside the pipe, but it's not uniform. I can tell you with 100% certainty there's static in your system. Some people may have more static than others, and it's not evenly distributed. Now, in this illustration here, you see these red patches. They indicate hotspots of static that randomly appear. And what happens is, here's this dig in on this pipe. This is kind of what you see in that ONG video. What happens is, as the gas comes flowing out of there, the broken edges that creates a lot of turbulence, and the static builds up on the inside edges of the pipe. The reason this pipe didn't ignite right away is because it didn't hit a hot spot. But the blowing out of the pipe, all of the gas flowing out of here over time, the static built up and up and up. It kept growing and growing, finally got high enough to arc to ground in the presence of the gaseous mixture, and that's what ignited it on camera. Now, it's the same thing if you have a purge pipe. You know, we're purging less and less, I get it. But and you're going to have the same thing with that, and the static is on the inside edges as the gas flows out. Now, this is the same if you have an overpressure vent or a relief vent. The same thing's going to happen. Now, this is a metal purge pipe, and you have it grounded. Now, you're assuming there's a connection to ground. You can't assume that. You have no way of knowing. If you have coatings or grease buildup, static can build up on those electrically isolated patches. So you should always look to dissipate the static on the inside edge of that purge pipe, and the connection inside. It's not going to be a smooth, clean connection between your metal purge pipe and the plastic pipe. Be careful when you remove the metal purge pipe. The connection there will have static on the inside edges also. The third most dangerous is cutting into a squeezed off plastic pipe. What happens is, downstream from a squeeze off, when you start the squeeze off process, the gas starts to accelerate to get through the narrowed opening. It's called the Venturi effect, well documented. And what happens is, the increased velocity creates increased friction downstream, which causes increased static electric charges, very, very high charges. So you have to be extremely careful when you cut into these pipe downstream. And it is the same if you're cutting downstream from a valve you've turned off. The same effect takes place. There was a valve that was opened in upstream in an upstream operation, and it was a steel valve, but there was static buildup. He opened the valve. They're apparently venting something, and it ignited. I don't think it was a fatality, but he was burned. So whenever you have a decrease or increase in the diameter of the pipe, whether it's a squeeze off or a valve, be very careful cutting into it downstream. Hot taps. Now, here's a perfect example why burlap is just such an old, antiquated technology. You fuse on the hot tap, and you need to dissipate the static because you don't want to cut into a hot spot in there, which is indicated by this red patch. Can't put burlap down in there. Well, when you have a topical anti-stat, you just spray it in there. Once you fuse the tap, you just spray it in there, and that anti-stat works down there to dissipate any charge. But when you have a hot tap, you've got to be careful. You don't know if you're drilling into a hot spot or not. And finally, whenever you cut into a pipe that's been previously under pressure, removed from service, it's been cut in or open, or you're reaching into it, you have to be aware that it could be a static hotspot inside there. I remember a Western operator telling me a story how they had a main line and a stub line coming off it. They were going to extend the stub line, so they shut the main line down, took it out of service. The crew went over there, they took a saw, started to cut through the plastic pipe. and boom, both of them were thrown out of the excavation and taken to the emergency room. Big bang. Well, it wasn't an explosion, it was an electrical shock. So the utility was embarrassed. They hadn't called for a locate, and they tell everybody to call it. They didn't call for a locate. So they called the gas company, and the gas company says, we don't have any lines out there. And what had happened, they cut into a hotspot on that stub line. This is an incident we're going to talk about now, and this is time we have an adult conversation. This occurred on November 26, 2014, Memphis Light Gas and Water. And the OSHA report reads as follows. At 10:30 a.m. on November 26, 2014, 5 employees were caught in an explosion due to a natural gas leak. Static electricity ignited the gas leak, and 1 employee was killed and 4 others were burned. Now, first of all, we're going to look at this a little bit further, but I want you to understand that OSHA did not find Memphis Light Gas and Water. They had procedures, they had training in place that this was designed, which is designed to prevent this. So it's important that you have these procedures and you do training in this, you audit it, make sure it's followed, and you will then have an affirmative defense if something goes wrong. This is a video grab of that ignition. Now, I'm going to tell you what I have anecdotally heard. This is being recorded. It's going to be on the internet. I have not verified this. So it has been alleged that the workers in the trench had squeezed off the poly pipe and cut the pipe. After they cut the pipe, it has been reported, alleged, that they then realized they had not enough room to do the operation they wanted to do, and therefore released the squeeze-off tool to move it back and re-squeeze the pipe. Remember what we said about the static buildup of squeeze-off pipe downstream. So if you're a manager out there and you don't really think static is a problem, I want you to remember this face. If you're a field worker out there and it's 5 o'clock on Friday and you're finishing up a job and you don't want to do that static suppression procedure, you want to get home early and have some beers with some friends, I would remind you, I would ask you to remember this face and reconsider your decision. Managers, reconsider your decision about enforcing your static suppression procedures. Field workers, reconsider your decision skipping them. 2 or 3 simple and effective static ignition prevention takeaways right now. Dissipate static on all exposed pipe, plastic and metal, from a safe distance. Distance is your friend. Be ruthless in compliance of your company's static suppression procedures. Managers and workers, don't allow any exception and field audit for compliance. Static electricity is very unforgiving of mistakes. Now, we're going to talk about static and metal pipe for a minute, because we're primarily talking about poly, because static and poly pipe is a far greater problem by the nature of polyethylene. But people think that you can't have static and metal pipe, and that is not true. The reason is because if there's any coatings, which everything's coated, or there's oil or grease, electrical insulating materials, or some kind of debris, that same friction that shears off electrons, those sheared off electrons in a metal pipe can be deposited and accumulate on surfaces that are electrically isolated, and they can build up. And so you need to be aware that you can have static and metal pipe simply because of all the coatings and all the stuff that's inside the pipe down the stream. Now, we're going to talk about a nice modern pipeline like this one you're seeing installed right here. And that is this Tennessee gas pipeline in Hanoverton, Ohio, in February 10, 2011. 10:30 at night. And if you take a look at this, if you see the flames on the left, To the left of that, you're going to see a shadow of something protruding up. That's a silo. This is on a farm in the middle of nowhere. Obviously, the pipeline failed. That's not the question. The question is, what could be the ignition source when it's 29 degrees, no wind, no weather, in the middle of nowhere? Got to have an ignition source. It's a metal pipe, right? Static can't be generated. Oh, yes, it can. It doesn't mean that every natural gas metal pipeline or every poly pipeline that leaks is going to ignite. However, it has the potential to do that. You must understand that. What's happened here, this pipe has failed. The friction of the gas going out the break, it's coated. The static starts to build up on the coated areas. It gets higher and higher the longer this gas flows out. It finally gets high enough to arc to ground and ignites a gaseous mixture, and you have the picture that we have. Now, one more thing about metal pipe. OSHA's reported 2 fatalities by explosions in the launching and retrieving of pigs. Downstream guys, you're not doing this too much. Upstream, they pig every day. They pig the lines every day. But if you are doing that, you must be aware when you have a launcher or retriever, you have the three ingredients for an ignition: gaseous mixture, exposure to ground, and personnel nearby. Whenever you get ready to launch a pig or retrieve it, you ought to spray an anti-stat inside the launcher or retriever before you begin the operation, so that when the pig goes in, the static is dissipated. When you open up, the static has been dissipated, and when you retrieve it and open it up, same thing. You have made an effort to dissipate the static charge. Now we're going to talk about the integrity issue that static causes in polyethylene system, and that's it creates electrostatic pinhole leaks. Now we're all concerned about good technology for leaks, so I'm going to just show you this in the newest advancement in LDAR technology for your consideration. Okay, what happens is when workers go out and they'll see these little fizzy leaks. Oh, they get a leak call at a house with a poly service. And they'll go out there and they'll see brown grass and they'll dig it up and they'll see just a little fizzy leak. And they'll say, just, bad pipe, just a random thing, No, no. It has been shown in the last 20 years that these leaks are caused by static electricity. They will be in one of two places. You will find them in the running in the flat areas of the pipe where it's arced through the pipe wall, or you'll see it'll arc through a bead. What happens in the fusion bead, if you have one in a service line, chances are you don't, but if you might see one in a bead because the fusion bead protrudes inside the pipe. The force of the gas goes through there, it hits that bead, the friction is higher, it builds up a charge, arcs through the bead. You might get a leak there. But most of the time, if you see a random leak in the middle of a line, it's caused by static discharge, and Gas Research Institute has proved it. Here's a paper published by Mark Staker about 30, 40 years ago about polyethylene pipe, how he found pinhole leaks in his poly pipe. It was published in the Proceedings of the Plastic Pipe Institute. Now, these occurred during squeeze-off. Remember, we talked about how when you squeeze off pipe, the downstream voltage, interior voltage gets so high it arcs through the pipe wall. Well, when he was doing a squeeze off, they soaked off and found these leaks. And they discovered that that's what was going on. The static generated by the Venturi effect during squeeze off, the static arced through the pipe wall and created a hole. However, this is not the only time it's been happened. I have 5 or 6 reports, a pinhole leak in poly pipe that was sent to a lab, and every single one of them from 5 different labs came back with the same conclusion, that it was caused by static electricity. It was not a manufacturing defect. This is a known DIMP issue. So if you are experiencing these pinhole leaks in your systems, you are required to deal with them. And we'll show you why in just a minute. This is a very important picture. This is a sectional view of an electrostatic pinhole leak. Now, I want you to see a couple things in this that are very significant. First of all, you notice in this yellow pipe, it's black in the inside, in the center of it. That's the leak. Why is it black? Because when the static charge discharges through the pipe wall, the heat of the arc of the electricity going through there burns the plastic, creating a hole, creating a channel. That black is burned plastic. That's one way you tell it's not a manufacturing defect. The second thing is you see how it filigrees out. You see all the little branches coming off. It's like a miniature lightning bolt. And that's exactly what it is. A manufacturing defect would not look like this. You'd have a bubble. You'd have a clean crack. You know, the slow growth pipe crack, slow growth cracks they had in pipe. They were straight lines, you know, there weren't any filigreed stuff like this. This is showing you that it is an electrostatic discharge that's causing these holes, not a manufacturing defect. Now, GRI says that these holes can be created in the normal transport of gas. Now, we don't know why certain areas have a problem. I can tell you there is a problem in Illinois. There's a problem in Indiana. There's a problem in Kentucky, Ohio, Western Pennsylvania, West Virginia, Virginia. Why there in other places? I don't know if it's because people haven't recognized what causes these holes. They're small holes, so they just don't bother with them. But if you have a pinhole leak in your system, that demonstrates you have static electricity in your system for this reason. If you have a half-inch MD poly pipe service line, because of the dielectric constant of polyethylene, I can tell you exactly what the voltage is necessary to arc through that pipe wall. It's about 42,000 volts. So if you have a half-inch poly line and you had a pinhole leak in that line, you had 42,000 volts of static inside that pipe that discharged to the wall of the pipe. Putting that in perspective, it only takes 3,000 volts of static electricity to ignite methane. A 3,000 volt static discharge hits 1,100 volts, which ignites methane. If you have pinhole leaks in your system, you got a serious static problem in there. Of course, the easiest way you find them is all of a sudden you get a leak call at the house. I smell gas. You go out there, and all of a sudden you see these little dots of brown grass going up to the meter. It's a poly line. It's an electrostatic pinhole leak. So pinholes always occur first in service lines because they're the smallest diameter pipe wall. Therefore, it takes the lowest amount of voltage to arc through it. However, I'll tell you a true story. Up in the upstream market, it's just the reverse of what you guys do in the downstream market. The downstream market, you take gas at 8 inches, reduce it down, distribute it to 4 inches, then do it, whatever you want, you know. But you go from a big pipe down to a little. In the upstream gas production and gathering market, it's exactly the opposite. They gather at wells at 6-inch lines, and they start to accumulate it until they take it to the gas processing plant. I got a call from a gatherer, and he had a 20-inch poly line, a gathering line, and he had a pinhole leak in it. One, imagine the cost to fix that. But two, can you imagine how thick the wall of that pipe was and what the voltage had to be to put a hole in a 20-inch poly line? So you're going to find these pinhole leaks are going to show up with leak calls in residence, with grass in your service lines. You're going to find multiples. It's rare that there's only one. If you got one, you got more than one. And the problem is, if they get close together, this gas pools to an unsafe concentration. And under 192, 1007, this is a known DEMP risk, and you're required to address and mitigate this. This was a photo sent to me by Fire Findings Newsletter. Fire Findings Newsletter is a newsletter circulated among fire investigators to educate them on causes of fire. And they sent this one to me because they couldn't figure out what happened here. They said, here we go. We got these houses. We're getting these meter fires. We can't find the ignition source. And here's what they said. There wasn't much question where this fire started at the gas meter and the incoming gas lines. While no traditional ignition source was nearby, the static electricity created by the leaking gas is likely led to a discharge, an arc, that caused the fire. You got to have an ignition source. Where's it coming from? That's why when you get these pinholes at your service lines, this is the possibility you can have. My first customer, when we originally started our system to get rid of these pinhole leaks, our first customer called us specifically for this reason. He was getting pinhole leaks of service, and he said, I'm going to burn somebody's house down. I can't do this. Now, also, you can get pinhole leaks downstream after squeeze off, and you can also get it downstream from polyvalve opening and closing. So it's important to keep that in mind. Whenever you open and close a valve, whenever you do squeeze off, you need to soap those downstream pipes to make sure that you haven't created a leak. Now, electrostatic shock to workers. I want to talk to you about incidents where guys can go to the, like that incident where they cut through that pipe and boom, off they went to the emergency room. Because of squeeze off, when you have some of these situations where you've got high velocity gas and it's blowing, at least you got to be unleashed until the external static is dissipated. Keep in mind that charge can go from the pipe to the worker to ground. Now, that's the same thing. Again, you have to be concerned when you have squeeze off valve open or closure, that same thing can happen. I have not heard of any reported fatalities from this, but a friend of mine, Steve Jocelyn, who was with Connecticut Natural for many years, he's now with PAL Controls, told me when he was in Connecticut, they had a guy who the static charge arced from the pipe to him, went through him and exited out his foot. They had to use a defibrillator on his heart, and he also lost his big toe. The big toe was burned by the static electric charge exiting his big toe. So although there's no fatalities, you got to take this serious. Can happen, just like when those guys cut through that pipe and they hit a hot charge in a hot spot inside that stub line, and off they went to the emergency room. Now, this is why tool grounding is important, but you must remember it is designed to protect the worker from getting shock. It does nothing to dissipate the static charge on the pipe. Remember, the poly pipe is non-conductive, and so if you ground that tool, it's only the charge that's in contact with the tool. That's the only thing that's going to get grounded. Grounding the tool does not get rid of the static on the outside of the pipe in the surrounding area. So it's important for you to remember that. It's important they ground the tool, but it's important to remember it doesn't dissipate static on the pipe. And again, remember when you're cutting into a pipe to be aware that you could hit a hot spot and get a shock on that. Also, when you have high velocity gas passage, like in this purging. Real quickly, I just want to mention one more thing that we've seen. It's something that you probably will not come into contact with, but in case you do, now you know. You'll be able to recognize it. And that is static electric charges can arc and burn out the low voltage electronics hanging on your system, whether it be a meter, SCADA devices, anything like that. I got a call a while back from the Kansas Corporation Committee. They regulate they're in charge of pipeline safety in Kansas. And this is what happened. They needed to locate a line for repair. So they hooked up the locating transmitter. They found the location. They dug it out. They squeezed off the line, and all of a sudden the locating transmitter burned up. And they said, well, we think it was the batteries in the locating transmitter caused it to burn up. Those are 6-volt batteries. They're not going to burn anything up. That's the reason they use low-volt batteries. What happened? Here's what I think is the most logical explanation. They squeezed off the pipe. There was a static buildup inside that squeezed off pipe downstream. It arced to the tracer wire, back up the tracer wire, and into the 6-volt locating transmitter and fried it. So if you're finding areas where you're getting meters that seem to get burned out, or you get some kind of equipment that is electronic equipment that gets burned out and there's no recorded lightning strikes, probably static electricity in your system. Okay, now we're going to talk about mitigation technologies. And basically the mitigation technologies are categorized by whether they get rid of the static on the outside of the pipe or the inside of the pipe. We have technologies for both, so we're going to talk about the external first. Back when the AGA recommended in their plastic pipe manual in 1974 to use wet rags, they did that because there was nothing else available. In 2010, we developed the IGT aerosol static suppressor. It's a topical anti-stat. What that means is on a molecular basis, when you spray this chemical in here, It hits the pipe and absorbs the electrons and neutralizes. It doesn't ground them. It's not soapy water in a can. You don't have to ground it. You don't have to wrap it. You don't have to ground it. You have to keep it wet. When you spray that on a surface, immediately the charge is dissipated. Now, on the external side, we make a system. It is not a liquid system like the aerosol. What it does is when gas passes through it, we suppress the internal static in the system. So no static is generated inside the system from the passage of gas. Now, external static separation is strictly a grounding mechanism. That's all it does. You wrap it up and you sit there and you keep it wet. And basically the water, the soapy water and the pollutants in the water, when you put it on the pipe, whatever area that rag touches, hopefully the charge is conducted through the water that the rag is holding and conducts it down to ground as long as there is a good ground. Now, the problem with this technology is one, you have to, the purpose of static elimination is to make sure an ignition doesn't occur when a worker's nearby. Yet with soapy rags, you have to send that guy down into the excavation before you've dissipated the static in order to dissipate the static. You don't want to do that. The second thing is you can't confirm that you've got a good electrical connection that's grounding the charge. You assume it is, you assume it's wet enough, you assume everything, but you don't know. You can't confirm it. The third thing, it's not suitable for a lot of operations, like hot tap. How in the world, it doesn't, burlap bags, you can't put them down in a hot tap. And then finally, it's only as effective as it's properly applied and kept wet. Topical anti-stat, what happens is it dissipates static immediately on contact with any surface. It could be a tool, anything. It's easy for field guys to do. I mean, think about it. It uses far less labor. Just imagine with me. Just do a thought experiment. You got a 6-foot section of pipe you've excavated, okay? He goes to the truck. He gets his bucket with his burlap. He goes down the trench. He starts to wrap the pipe. He takes the pipe out. Starts to wrap it around. He pulls it around, reaches around under there and pull around, reach around and pull around. And he does that all this 6 feet, say, okay? And he stakes it and then he gets it wet, okay? Now, that guy's getting paid, what, 35 an hour, burden rate, probably 125 with benefits, all that, okay? So that guy probably spent 15, 20 minutes of labor putting on free burlap. Okay, you take that same 6 foot, you take a can, topical anti-stat, and you go, you turn the can upside down, on the bottom, and in about 30 seconds, you're done. So you've saved about 14 minutes of labor. So topical anti-stat, even when it dries down, continues to dissipate the charge. You don't have to keep wet. You don't have to watch it and monitor it. It works automatically. And it's suitable for any kind of operation. Hot taps, purge pipes, you can use it anywhere. Our aerosol was tested by the Gas Technology Institute to make sure it doesn't affect PE. It doesn't affect fusing. It's non-flammable. There are some commercial consumer anti-stats on the market. Do not buy them. Okay, repeat, I said, do not buy them. And the reason is the gas they use to push out the anti-stat is propane. We do not use propane. We use nitrogen. Our aerosol is really essentially a fire extinguisher. It pushes away the oxygen when you spray it near that surface. GTI said it's as effective as wet burlap, and there's no legacy issues. So the third and final simple and effective static ignition prevention action, ditch the burlap. Get rid of the burlap. It's 50-year-old technology. It's expensive for labor intensive for you to use. That's why we have new technology. Now, remember, we've been talking about external dissipation, static dissipation. Burlap or our aerosol does not get rid of the static on the inside of the system. It can't. It can't penetrate the poly to get inside there. So it's important you understand, don't get into a false sense of security by saying, well, I have no risk at all because I've dissipated the exterior static. You must dissipate the exterior static just as a safety measure, but it is not 100% foolproof. Interior static suppression solves that problem. Now, we have a system that dissipates static. It's been out 12 years now, and it dissipates static. Gas passes through our cartridge. Around our cartridge is housed, like you see that housing on the right, that's at a gate station. Gate comes in from transmission, runs through our cartridge, goes on to distribution. And what happens is When it passes through our cartridge, there's no liquids or anything. It suppresses the static in the system from the time it goes through our cartridge to burner tip. Well, my oldest customer was having the pinhole problems. He has no pinhole problems anymore. But he has about 8,000 services, 350 miles. He has 2 cartridges. That's it. Treats the whole system. It works out to be about 50 cents a service a year. So it's really like cathodic protection from polypipe. The reason he put it in is it dissipates the static inside the system. When we first developed this technology, we had Nicor put it in a residential area outside Illinois, and they monitor it. And what happened is we were able to make static come and go in this area simply by bypassing our system in and out of it. We could control it, make it come and go at our will just by bypassing our system in and out. But the main reason people put it in now is to stop the leak calls and the repair costs on poly service lines caused by pinhole leaks. So really, you can kind of consider this, it's cathodic protection for polypipe, but it has a secondary benefit. It's static that's putting holes in your pipe, but it's static that ignites those blowing lines. You have the secondary benefit. In addition to stopping pinhole leak creation, you greatly reduce the risk of internal static igniting blowing gas, leaking gas. So here's your crew. They're ready to go out Monday morning. So what I'm going to do is just wrap this up and give you a review of the O&M best practices. First, spray all exposed pipe, poly or metal. If you got third-party damaged pipe blowing, spray. That's one of the most dangerous that you're going to have. Dump anti-stat in it. Don't worry about them. Dump anti-stat on the ground and as close you can to the blowing line as you can to dissipate any static, to mitigate any static. It's not perfect, and then once you get the line shut off, use our reach tool, spray anti-stat into that cut before you get near it. Check for pinholes after squeeze off, always. And also, if you have poly downstream from a valve, check downstream for an open and closing valve. Be vigilant for shock wrist during and after poly squeeze off and valve opening and closing. Tool grounding is a worker protection, do it, but it's not a static suppression procedure. Final review of main points. Static, you should presume static's present in your system. Again, it's been shown time and time again. Presume it's there. Don't be naive and think the other guy's got a problem. That's not the case. External static suppression only gets rid of the external static. It does nothing to get rid of the internal static. Pinholes are not a manufacturing defect. I have yet to get one lab report to say it was. The electron microscopes say it's not. It is due to electrostatic discharge. It's static buildup in your service lines. You can't get rid of them unless you put internal static suppression in. Static ignites gases, it shocks workers, it creates leaks, it burns out electronics. If you deal with static, these 4 problems go away. So, thanks for your time. If you want to get in touch with us, here's my phone and email. If you'd like us to do this presentation at your gas association meeting, just contact me for dates. If you're interested in an aerosol static suppressor, email or call for a local distributor. You can call for us or us direct. We have an online store. And if you are interested in our internal static suppression system, just call or email for no obligation quote. We can explain how it works, and you can see if it's worthwhile. Like I said, generally works out about 50 cents per service per year. Maintenance is simple. Once a year, we change out the cartridge. It works automatically. That's it. So with that, thanks. I hope this is helpful to you. Any comments or anything, just send me an email, dsmith@ionixgastechnologies.com. Be very interested in any comments. If I missed something, it always helps improve these presentations. So you have a wonderful day. Thanks.